This week, we are changing topics to, I'm going to go out and say it, this is the most important week of the class. What you learn here is one of the most important tricks of the trade. It's called, I'm going to write it up on the board, the singular value decomposition. This week's lecture's focus on this is going to basically introduce you to this really amazing data analysis tool. It's all linear algebra, as always. But what you can do with this is quite remarkable. So in this first lecture, I'm going to introduce you to this singular value decomposition. And by the end of this week, I'm going to show you how you can use this to do things like start thinking about how you might do image recognition software for faces, for classification, dogs versus cats, and all kinds of interesting ideas that come out of this singular value decomposition. Extremely powerful, extremely useful in a lot of contexts. And so let's begin, and let's start thinking about what this thing is. So first off, let's think about what linear algebra does and what a matrix does to a vector. Okay? I'm going to take as an example the following vector, 1, 3. Okay? I'm going to show you all the ideas in two-dimensional space, and then we're going to generalize it to higher dimensional space. And I'm going to take a matrix A, which is just the following. I'll just make this stuff up. Okay? So I take these two things, and what I want to do is think about constructing a vector y, which is just simply a times x. So this is just a matrix times this vector. It's a simple procedure. We've been doing this all quarter. And what does it give you? Well, if you do this multiplication out, right? This times this, which is 2 plus 3. This times this, that's a negative 1 plus 3, 2. Simple. No magic. Very straightforward idea. But let's start thinking about what this does graphically. So let me draw sort of our typical Cartesian coordinates. And if you notice, the vector 1, 3, right? So if you go over in some coordinates here, vector 1, 3 is sort of a vector that goes right to there. And what this matrix A does when you multiply it is it produces a new vector y, which is in the direction 5, 2. 1, 2, 3, 4, 5, 1, 2. Right about there, something like this. So big deal. You transformed one vector to another. So one way to think about this process is that what you actually did is you took this vector x, you rotated it, and then you stretched it. And in fact, any kind of process like this, what A really does is it rotates and stretches vectors. That's all. Rotation and stretching. So, and I've shown you this. So one way to think about it is if I, again, just to show you this, let me take this thing here. Let me draw sort of a ball of the same radius here as this thing here. And you can see what it did. It rotated by some angle theta to here, and then you stretched it out a little bit. So are there matrices, for instance, that capture these two fundamental ideas of rotation and stretching? Well, if you want to rotate any matrix by an angle theta, then there's this very well-known matrix. It's called the rotation matrix. This is in two dimensions, and here it is. Let me write it down. That's it. This matrix here rotates any vector by an angle theta. Okay? So that is what this represents, a rotation by theta. All right? Now, the stretching is something different. Just all you need to do is think about a matrix. I want to take a matrix now and stretch this vector. Okay? Well, an easy way to do that is just to create the following matrix. That's it. Where alpha is your stretching. Okay? So one way to think about A is that A itself is made up of some combination of rotation and stretching. Okay? So a little bit of this matrix plus a little bit of this. In this case here, there's some angle theta you rotated it through, and then you stretched it, so alpha is bigger than 1. So by the way, just to see how this works on this, so suppose I wanted to stretch this vector here by a factor of 2, make it twice as long, then I can make alpha as 2, and then I'd get a new vector, 2, 2, 0, 0, 1, 3. And if you do this multiplication, right, you take this times this is 2, 0, and then 6, right? So it's the vector 2, 6. Well, the vector 2, 6 is just twice as long. That's it. So you can see that this thing will just stretch. If alpha is bigger than 1, it stretches it. If alpha is less than 1, it compresses it. If alpha is 0, it makes it 0, of length 0. Okay. So these are kind of fundamental ideas to have in your head, that when you manipulate a vector with a matrix, what you're actually doing is nothing more than rotating, stretching. That's it. Okay? All right, so this starts getting us to the idea of the singular value decomposition. And in particular, we want to think about what happens to a circle under a matrix multiplication. Okay? So let's go ahead and take some kind of circle. And in some coordinate system, let's say I can represent this with some orthogonal components, v1, v2. And this is, by the way, in 2 dimensions. But you can think about going to higher dimensions. In fact, so this is 2 dimensions. And we want to think about n dimensions as a generalization. So think about this as a circle in 2 dimensions. In 3 dimensions, it's a sphere. In 4 dimensions, or 5 or 6 or more, they're called hyperspheres. Okay? But it's the same idea as this. And then I ask the following question. If I take a matrix A, which is some kind of matrix which is an m by n matrix. Let me write it down here so I can get all my notation correctly to what I want. So this is just an element of a m by n matrix. I can ask the following question. What happens to a sphere under this matrix operation? Now in this case here, this is, since it's 2 dimensions, it's not going to be m by n. It's going to be a 2-dimensional matrix. Like what happens to these vectors when you hit it with a matrix multiply. Let's take this out for a minute. And what does happen? Well, I just showed you what happens to a vector. Let's come back to the other board for a moment. You give me a matrix A, and I ask, what does it do to a vector? What it does to a vector is it rotates, and then it either stretches or compresses it. That's it. Okay? That's what the matrix A does to an individual vector. By the way, it takes any vector and it rotates it by the same amount, and the stretching is the same amount. Okay? It's linear, so it's not like it acts differently on different vectors. For every vector, it rotates it by a certain amount, stretches it by a certain amount. So what happens to the image of a circle, or more generally, to a hypercircle or hypersphere in these dimensions? So I'm going to work in some sphere. Let's call this some sphere S. And I'm going to hit this thing with a matrix A. I'm going to ask, what happens to that? Well, what it's going to do is going to rotate the sphere and stretch it. Well, what happens if you take a sphere and you stretch it? It becomes an ellipse. So this thing here, generically, under the stretching process, becomes an ellipse. Okay, so you went from a sphere to ellipse. There was some rotation. And then, how do you quantify an ellipse? What are the key factors in thinking about representing an ellipse? Typically what we think about is, and you learned this very early on about ellipses, there is the major axis and the minor axis. So I can think about, there's my major axis, there's my minor axis. Actually, let me draw it consistent with my notes. Okay, major and minor axis, and what I can do is think, oh, those are a new coordinate system for me. So I started off with the coordinate system over here, orthogonal directions, v1 and v2, in 2 dimensions of like this. But remember, I'm thinking about this as sort of a really, in my higher generalization, is I have an n-dimensional sphere. And what I did is I transformed it by a matrix multiply. And what it did, all the multiplication does, is it rotates and stretches. Okay, that's it. That's all a matrix multiply does. So I get into this space here, where now I can say, well, let's suppose I have some unit vectors along this direction and this direction. The unit vector along this direction, let's call that u1. The unit direction along here is u2. And the distance along there, I can think about, well, then this whole thing is some parameter sigma 1 times u1. This is sigma 2 by u2. So u1 and u2 are unit vectors. They tell me which direction it's going, and sigma 1 and sigma 2 tells me how much in that direction I'm going. Okay? So for convenience to think about this stretching operation, remember, A is an n by n matrix. And now what I do over here is I have u1 and u2, but more generally, this n-dimensional sphere takes me to an n-dimensional, whatever, it's called a hyperellipse. Okay? Let me make this arrow a little more pointy. All right. So I started off in a vector space spanned by v1, v2, all the way to vn, and I ended up in a new vector space, u1, u2, u3, all the way to u of n. Okay? So this is generically what happens. That's if A is full rank. What I mean by that is, you could always imagine if this is rank deficient. In other words, if I think about the number of rows or columns that are linearly independent, then I could imagine a case where I act on this and I go to a smaller dimensional space just because this thing only acts in certain dimensions, as it were. Okay? So I have this new representation of orthogonal sets, and in each direction there is the amount of stretch in that direction. So these are unit vectors, orthonormal, and these are your stretching factor. So there you go. I took a sphere, and under the matrix operation, it stretches with some rotation into a new set of coordinates which the stretching factors and those coordinates are given by these values here. So these are the principal axes. So the one way to think about this is these are your principal axes, okay? Or principal semi-axes. And the stretching factors are going to be called the singular values. Okay, so it's really important to try to understand this sort of in a fundamental point of view. Hopefully this kind of makes sense. It's just matrix multiplication. All you did is you took a vector or took a set of vectors, you rotated them, you stretched them. That's it. Okay? So that's one way to think about it. And again, here it is. Here's the main idea. Take a vector. When you multiply this thing, you rotate, you stretch. Okay? That's what you're thinking about doing here in a simple 2 by 2 example. And all you're doing is saying, well, instead of 2 by 2, let's go to n by n. And let's not just take a single vector, but a whole set of basis vectors for this system into what happens in this new stretch coordinate system. And this is it. Okay? So this is the idea. You go from one vector space here, v1 to vn. Under matrix multiplication by A, you get to a new vector space, which is just, now you're living on this stretched and rotated ellipse, where now u1 through u of n are your basis vectors there, the unit vectors there, tell you the directions. This is now your new x, y, z coordinate system that's orthogonal to each other. And sigma 1 through sigma n tell you how they've been stretched by this specific matrix A. Okay? All right. So let's write this down more formally. When you think about this thing taking the A, you're going to take this A and multiply it by V. You're going to start creating the structure you want to play with. Okay, so let's come over here and represent this. Okay. I'm going to switch pins. See if this one's a little darker. So what I want to do is think about the matrix of A acting on one of these matrices, let's say V1, and it should produce sigma 1, U1. In other words, take A, act on V. What does it do? It rotates and stretches to a new vector U of length sigma 1. Remember, U is a unit vector. Its length is 1, so you need the sigma 1 there. Now, the first thing I want to point out about this is, doesn't that look a little bit like an eigenvalue problem, right? Usually the eigenvalue problem is written down like this. So you kind of have a lot of the same elements. You have a matrix A, you have a vector, is equal to some constant. In this case, the constant would be lambda, would be sigma 1. But now, here's the big difference. You have a U1. Normally in an eigenvalue problem, it'd be V1 and V1 over here. Now you can have a different vector over there. V1 produces U1. Okay, so it's not one of these, but there's definitely a very intimate relationship between this and the eigenvalue problem, which I will show you in just a moment. So this is how it acts on a single vector. So you can imagine, well, how does it do on all the vectors? Well, here's how it does on all the vectors. Each one does this. The v of j produces the u of j times sigma j. A really nice way to write this is, if I write all the equations down at once, is the following. So I'm going to write all these, there's n of these equations. So let me try to write it in a form that kind of makes sense. I consider the matrix A. And it's multiplying what? Well, V1 and then V2 and V3. So let me think about this. V1 and then V2, V3, all the way to V of n. Okay? So first thing here, if you remember, A itself is a matrix of m by n. And to do this multiplication, V itself is n by n here. In fact, look at this. The columns of this matrix are V1, V2, V3, V4, all the way to V of n. So this has n columns, and there's n rows. So this thing here should be a n by n. So that's this left side. Is equal to, well, in the first case, here, let me write it in this way here. So it's equal to sigma j, u sub j. So first I'm going to put in here u1, u2, all the way to u of n, times, now I have a diagonal matrix with sigma 1, sigma 2, all the way to sigma n, 0 everywhere else. So for instance, think about the first row of this equation. It's A times V1. A times V1 produces U1 times sigma 1. That's that first equation. The second row, A times V2, produces U2 times sigma 2. That's the second of these equations, and so forth. So this here is a nice representation of all of these together. Okay, so this set of equations can be very conveniently represented this way. You take all the v vectors, you stack them in columns. Take all the u vectors, stack them in columns. This is a diagonal matrix where the sigma is along the diagonals. And so one way to think about this is just say, well, if I have that, then this thing here is the matrix A times, let's call this a vector matrix V, is equal to, call this matrix U hat, and I'll tell you why in a little bit, and sigma hat. Okay? All I've done is written this set of equations all together here and like this, and this is how you would write them in a very shorthand way, in a matrix multiply way. The matrix A times V, where V, the columns of V are all the V vectors you had before, is equal to matrix U, which is all the new vectors in this hyperellipse space, times sigma, which are these singular values, the stretching factors. A couple things I want to point out. I'm going to assume that these V's are basically orthogonal orthonormal set, right? That's kind of how I drew it. Let's come back over to here, right? So the V1 and V2 were these orthogonal directions, unit length. That's why it's a circle. So these are orthogonal coordinates that get transferred to here to another set of orthogonal coordinates, U1 and U2. U1 and U2, remember, are unit length and are orthogonal to each other. So I went from one orthonormal basis to another orthonormal basis. Okay? So what you can think about is all you did with this matrix A, at least in terms of V producing U's, is that it was a rotation. That's the rotation piece. When you go from V's to U's, remember, A produces rotation and stretching. All the stretching is picked up by the sigma. All the rotation is picked up by the U's. So one way to think about this matrix here, then, is to say, well, the V's, this is like a rotation matrix. This is also like a rotation matrix. And this is your stretching. Now there's a fancy name for a rotation matrix. It's called a unitary transformation. And if these are our orthonormal components here, and we think about this then as a rotation matrix, then what ends up happening, there's some special properties of this matrix, which is the inverse of the matrix is the same as its transpose. So in that case, the big deal about a unitary matrix is that V minus 1 is equal to V star, which is the complex conjugate transpose. Okay? So that's the way you want to think about it. This is a rotation matrix. And if it's unitary, this holds. Same thing with this. The inverse of that matrix is transpose complex conjugate. So actually finding the inverse is trivial. You just simply transpose, and anywhere you see a complex I, you turn it to minus I. That's it. So you can easily get your inverse for the matrices. Okay? All right. So hopefully everybody's good at this point. It is very important that you understand from this formula here, or this formula here, for there's n of these, right? I'm acting on each of the n directions of V to produce new n directions in U with a straight scaling factor, stretching or compression. And then if I combine all n equations together, generically it looks like this, which in matrix form is right there. Okay? Kind of convenient. So let's go back over here and talk about what this means. So let's write this down. A V is equal to U hat sigma hat. Now what I'm going to do with this is to multiply both sides on the right times V inverse. So A, V, V inverse, that's 1. That's the identity. So this is equal to A times I, which is equal to A. So that's the left side. The right side is U hat sigma hat V minus 1. But if you remember, the inverse is the same as the complex conjugate transpose, V, okay? So that gives you U hat sigma hat V star. This is called the reduced singular value decomposition. So what does it say? My matrix A. What do matrices do? Remember, what do matrices do? They rotate and they stretch. That's all. So how do I get the rotations and stretchings of this matrix A correctly? Well, A is a rotation times a stretching times a rotation. So the idea is that this decomposition exists into these 3 component parts. Okay? So I've replaced one matrix by 3. Okay, but this is kind of important. So let me try to draw graphically what this thing looks like. The matrix A, if you remember, A itself is a m by n, okay, is equal to U times sigma times V star. Okay? So that's kind of the generic description there of this matrix. So this here is some kind of, this is an m by n here. And all this means it's a set of complex numbers that's n by n. This thing here is also, this is actually m by n. And then this thing here is, oops, it's an element, not a, it's an element of, this thing here is m by n, and, or actually m by m, okay, m by n, and that thing there is m by n, okay? Actually, excuse me, that's n by n as well. Okay, this is in the reduced form. And remember, this thing is diagonal, so it only has entries along here, this diagonal term, but this can be full, this is full, and this is matrix A. So this is what's called the reduced SVD. The more standard way that people often think about the SVD is to say, okay, I have this m by n matrix. This is m rows, n columns. So in some sense, it's like an underdetermined matrix. Okay? So at most, I have n columns. It's only going to span an n-dimensional space. One thing I could do is add some what are called silent rows. So I take my rows that I have, and I add, so remember I have here n of them, and I add m minus n, so that this thing here now is m by m. It's full rank, square matrix. Does it matter if I add these? Remember, these are n orthogonal directions, and all I'm saying is, well, okay, if there's n orthogonal directions, I can make up m minus n other orthogonal directions that are orthogonal to these. It doesn't cost me anything. I can do that. And then I can also stretch my sigma matrix accordingly. So there's my singular values. The rest down here are all zeros. So this was sigma bar. This was v bar. And then v itself is here. Sorry, this was v hat. That was u hat here, sigma hat v star. This is now the new u, which is m by n, m by m. And then now this sigma here, which is not sigma bar, it's an element of m by n. And then this v star is an element, it's still n by n. Okay? This is called the singular value decomposition. Okay? So you take a matrix A, you represent it as some matrix U times singular values C, which are the stretching factors, times V star, which is the complex conjugate transpose, or the inverse, V, which is n by n, m by m, m by n. Okay? Now, normally the way you order this too is that when you do the singular value decomposition, it's always ordered in the following way. Biggest to smallest, all singular values are equal to or greater than 0. There are no negative singular values. They're all positive numbers. Positive real numbers, ordered biggest to smallest. So when you think about this, biggest to smallest on down the line there. Okay? So this tells you the stretching in every single direction. So you take this sphere, and if you transform it, it's like stretching it in some directions. And how you rotate is telling you is being basically dictated by these two matrices, and how you stretch is being dictated by this one. That's it. Now, there's a theorem concerning this that I think is very important to write down. So let me write it down. And this is also going to be a big difference between an eigenvalue decomposition and this. Okay? Every matrix A has a singular value decomposition. Okay? So full stop for a moment. A lot of matrices, you try to decompose them, like we've talked about LU decomposition, eigenvalue decomposition. Those aren't guaranteed to work for every matrix. If you have a matrix that's singular, for instance, LU won't work. If you're doing eigenvalue decompositions, similar kind of things, it only works in certain cases. SVD always works. Always, always, always. Okay? There's never an exception. You can always do a singular value decomposition. Moreover, the singular values given by this set, sigma j's, are uniquely determined. Okay? And if A is square, okay, the sigma j are distinct. Okay? And the singular value, and then also the singular vectors, u of j's and v of j's, are also unique up to a complex sign. Okay? This thing always works. It always produces for you singular values that are positive in order from biggest to smallest. And it always produces you, those are unique. Same thing with the unique eigenvectors, or sort of unique singular vectors u and v. Okay. So the question then comes, how do you compute from a matrix A, this matrix U, the matrix V, and the matrix C? So in other words, remember, you're saying my matrix A always has this decomposition. And the question is, how do I compute these things? What's the formula to being able to compute this? And here is where we show you how it relates to eigenvalues and eigenvectors. Okay. So, think about the following. A transpose A. One thing to think about. If I want to compute this SVD, this is where this is going to go towards. Well, A transpose A, well, A itself, right, is U sigma V star, and then I have U sigma V star, and I'm taking the transpose of that. Well, the transpose switches the orders, okay? And so what I end up getting, if I do this, it not only switches the order, but I'm taking the transpose, well, actually, it also takes stars, unstars it, and puts stars here, so then you get something like this, V sigma U star. That's what you get when you transpose this thing here. It switches the order of multiplication, and then it transposes these, but that star really means transpose. So you transpose that, and you transpose a transpose, a transpose just gives you back the V itself. Times U sigma V star. But if you remember, U star times U, well, U star is basically, because it's a unitary matrix, it's a rotation matrix, U star is equivalent to U inverse. U inverse times U is 1. So what do you get? V sigma 1 sigma V star. Well, this is 1, so you just get sigma squared there. Okay? There's that. to keep in mind. And then I can say, OK, that's one observation. So let's take A transpose A times V. Well, this is A transpose A, V sigma squared times V star times V. But what is V star times V? 1. Because the transpose of this unitary matrix is V to the minus 1. This times this is 1. And so you end up getting here V sigma squared. This is A transpose A V. And this is an eigenvalue problem. This is AX equals lambda x, right, in our standard way to think about eigenvalues. So here, the lambda is this sigma squared. The x are these vectors here. And the A now is this matrix there. So it's an eigenvalue problem. So if I solve this eigenvalue problem, what do I get? The eigenvalues, lambda, are like the lambda j's are like the sigma squared j's. So that's great. So if I can find the eigenvalues, they're going to be equivalent to sigma j squareds. And the eigenvectors are V. That's how I get V. How would I get U? If you get U the following way, A times A transpose. Well, A times A transpose is U sigma V star times U sigma V star transpose, which is U sigma V star. Remember, the transpose here flips the order and transposes, so it gives you a V sigma U star. V star times V is 1. You get U sigma squared U star. Multiply now both sides by U. If you multiply both sides by U, what you end up getting is the following. That's 1. So you get A transpose U is equal to U sigma squared. Eigenvalue problem. Same eigenvalues as here. So the singular matrix sigma is the same for both, but notice when you solve this eigenvalue problem of A transpose versus A transpose A, what you end up getting are the eigenvectors give you the matrix U. This eigenvalue problem, this is how you get U. Right? You solve for all the eigenvalues. One other thing to note is that you always know you can solve this because by doing A transpose, what you've effectively done by doing this is this matrix here now becomes what's called self-adjoint or Hermitian, which guarantees that in fact the eigenvalues are real and positive and distinct, which you already know to be the case for these. Okay, so you get the eigenvectors U. Eigenvectors of this eigenvalue problem gives you U. You can also get your eigenvalues, which gives you your singular values. And from this one over here, you can get eigenvectors of V. OK, so that's how you would compute this U and V to begin with. Now, so far, all we've talked about this is essentially this decomposition says what I can do is a matrix A. What do I know what to do? I know that what it does is it rotates and stretches. In particular, if we come back over here real quick to finish off, the matrix U, when it acts on a vector, it rotates, stretches, rotates. Okay? This is, from the simple example I gave at the beginning of class, you know that's all it does. Rotates and stretches. So here's a formula for doing it. You're always guaranteed to do this. But what you can do with this thing is magic. So what we're going to learn in the next couple lectures is what this thing can do for you in terms of solving data analysis problems. And that will be the topic for the follow-up lectures on the singular value decomposition.